Are you all able to see my PowerPoint presentation?
Yes, sir.
Yes, sir.
Okay, so I'll just try to go to the next point. Did that refresh? Did you see some other point come in here? How to get physical systems to do your bidding?
Yes, sir.
Yes, sir. That's visible now, right? Okay, excellent. So then I think this thing is working. For some reason, last time it was not working. Now it's working. So let us get started. Today's lecture is actually a popular talk, partly because the first week the students often would not have decided about the schedule and so on. So I don't want to get started with the technical parts of the course right away. So I just thought I will give a popular lecture on the history of automatic control systems. So it's also actually, the primary goal was, as I said, to fill in for, to not start the technical stuff right away, but along the way, when I presented this the first time and later, I realized that this actually is a useful way to build some perspective as well about the subject and how it has evolved over a period of time and where we want it to go. So it's actually not as trivial and not as much of just a purely entertainment thing that I had imagined it might be. So with that small introduction, and hopefully you would partially at least agree with me towards the end of this course, toward the end of this lecture. So this lecture is about, as I said, history of automatic control systems, and in other words, to answer this question of how to get physical systems to do your bidding or to dance to your tunes or to obey your commands or whatever it is, and primarily in the face of uncertainty. Okay, that's the operative word here, uncertainty. So as we discussed, controls as a field is far more general than just looking at ways to get systems to do your bidding in the face of uncertainty. If there are no uncertainties, you can still, there is still relevance for control, but it becomes particularly important in the face of uncertainties. And in that scenario, it is the feedback style of doing control that becomes very relevant. So this is a brief history of how this subject has evolved over the last several centuries, actually. But before we even go back to 4 or 5 centuries, or maybe higher, maybe more, we should actually go all the way back to the beginning of life itself. Because if the proper way to start the subject is by paying obeisance, by acknowledging the fact that Mother Nature was the first control engineer out there. Because if you think about it, our planet, despite being hospitable to life, is actually quite a hostile place. You have in any given region, you have huge changes in conditions during the year, and you have huge changes in conditions not just during the year, but sometimes even during a day. So you have cold evenings, and then hot afternoons, cool mornings. Then as seasons progress, you have sometimes snowfall if you are in a temperate region. It can be swelteringly hot if you are in a tropical region. And then you have warmer climates. Sometimes you have to deal with other seasonal uncertainties such as flooding and so on and so forth. So in other words, the world around us, the biosphere, is a rather uncertain place for us to be in. And that can be testified even by the weather forecasters. They have to deal with routinely the embarrassment of making predictions and see that their predictions don't come into fruition. Despite all the computing power that they have at their disposal, very frequently they get predictions wrong. And that's simply because of the complexity of the system and the associated inherent uncertainty with which all life forms have to exist. So Mother Nature, therefore, has found ways, has invented ways, or has evolved ways along the way to make sure that the internal state of an organism is maintained more or less constant regardless of how much fluctuation there is in the environment around this organism. Okay, so and this has been packaged into practically every single organism, some to greater sophistication, some not so sophisticated a manner, but nevertheless invariably you will find, starting from plants all the way to animals, you will find this feature of some resilience, some way to adapt, some way to change, some way to resist changing entirely in response to changes to the outside environment. The best example of this in the animal world is human thermoregulation. Not just human thermoregulation, but thermoregulation of many animals, in particular mammals and birds. So all these animals have this unique feature of keeping their body temperature within a very narrow window, right? So our body temperatures rarely fall below 36 degrees and rarely exceed 37.5 degrees. If it exceeds a little bit beyond that, you are said to be in fever, and a little bit more beyond that, and then your internal body parts will start to malfunction and you will die, right? Similarly, if the body temperature falls below 36 degrees, it's called hypothermia. That can sometimes happen if you want to take a dip in a very cool pool. So this happens in tropical regions. So where the lakes could be at freezing temperatures, but still would be liquid. So it looks very alluring and and attractive. So you try to jump into the lake to swim about and cool off, and all of a sudden that sudden loss of temperature, sudden reduction in body temperature could be such that within no time, before you know that something is going wrong, you would be dead. So many people who die of hypothermia would have lost their life so quickly that you don't even sometimes see any anguish, any sign of alarm on their face. So clearly, therefore, human thermoregulation has helped us to survive on this planet. Not just us, as I said, other mammals and birds and so on. And they partially explain the success of these forms of animals in colonizing different parts of the world. So in Antarctica, for example, you find penguins, but you don't find snakes and alligators. Why is that so? That's because penguins have this innate ability to maintain their body temperature. Of course, it's also augmented by a very thick layer of fat and their tendency to huddle together and so on. But fundamentally, they have the ability to maintain their body temperature, and that's how they're able to function. And many birds have colonized the Arctic and the Antarctic regions. You find polar bears in the Arctic, again a mammal. So all these warm-blooded creatures, as they are called, have managed to colonize parts of the world that are otherwise off limits to animals that do not possess this talent. So on the right-hand side, therefore, you see a thermal image of a snake which is coiled around a human hand. The human hand looks orangish yellow in color because it's at a high temperature. It's at 37 degrees or 36, 37 degrees, whereas the snake is a cold-blooded creature. So its body temperature can change with the ambient environment. In fact, it has to bask in the sun and warm itself up every time before it can get active. So at this instant of time, it has not yet undertaken that activity. Therefore, it looks dark in contrast to the human hand. Okay. So this explains how we have been able to beat other forms of life, in particular reptiles and so on, in colonizing different parts of our world. And if you think about it, it's not just temperature alone that is maintained constant in our system. All other chemical concentrations and other things are also maintained constant. So if you return for a moment to the temperature itself, how do we maintain temperature a constant? So if we get cold, then we shiver. So the act of shivering helps generate energy, helps generate heat, and helps to raise up the body temperature. So the heart, the liver, and the muscles all play their role in keeping us warm. Similarly, when we have to cool off, when we are overheated, then our blood vessels expand in size to allow for larger flow rates of blood through them. And blood now acts like a coolant. it takes heat away from within the body and delivers it to the extremities of the body much faster as a result of the highways having been expanded in some sense. Okay, and therefore it can exchange heat to the environment much faster and cool off the body. So this is called vasodilation. Then there is perspiration. We all know that we sweat. And there is salivation. So there are some animals which are not blessed with the ability to sweat. For example, the dogs do not have glands that help them to perspire, so they salivate. So the saliva, the evaporation of saliva, takes away energy and cools down the animal. So as I said, there are limits to to the range within which this control system can work. It's 25 degrees to 55 degrees. Beyond 55 degrees, we die of hyperthermia. Below 25 degrees, we die of hypothermia. And coming back to whatever I pointed out earlier, there are other chemicals also in our system which we regulate. So our blood sugar, for example, is regulated. So insulin and glucagon are these two chemicals that help to regulate blood sugar. So insulin takes away excess sugar and glucagon injects sugar if there isn't enough of it. And if you are deficient in production of insulin, you have too much sugar in your blood, and that's when you get diabetes, right? So you fall sick. More generally, there are several other bodily functions, chemical concentrations and other flow rates, etc., which are maintained constant in our body. And there's a name given to this tendency of all life forms to maintain the internal state irrespective of the external environment. And this is key to their survival. And this is called homeostasis. And there's a separate branch of knowledge called metabolic control theory, which is devoted to understanding how enzymes help to maintain homeostasis. If you look at this entire machinery of maintaining homeostasis in an individual animal, it looks unsurprising on second thought, because you expect that such a mechanism is probably necessary to actually keep such a sophisticated animal as a human being or an elephant or whatever else alive, despite all these uncertainties with the environment in which they live. What might surprise you, however, is that over several thousands of years that life forms have existed, some very strange feedback control systems have evolved as well. Things that we don't expect to see, but as a consequence of being favored by natural selection, they exist now. And let me briefly talk about one of them. And this is the example of pest control in plants. So two very unlikely organisms coming together, to implement feedback control. So on the right-hand side, what you see is a picture that I have pasted from a garden. So it looks very idyllic. You have very beautiful flowers there. You have all butterflies flitting about from flowers, one flower to the next. And of course, we know that flowers are the sexual parts of a plant. It is used to lure. So the plant lures the insect by promising it a small drink of sugar solution, an energy drink essentially, like Pepsi or Coca-Cola. And in exchange, it gives it a package. It uses the insect as a courier. The package essentially is the pollen, which the insect is expected to deliver to another flower of the same species, a female flower, and thereby fertilize it and then help to propagate the plant. So that's the role of the flower. And plants have very successfully enlisted insects as couriers by promising them these small energy rewards in exchange for their existence. But insects, on their part, are seldom, very neutral or just merely helpful couriers. They can often do their own damage. So, for example, in good time, once the butterflies have had their drink and they are energetic enough, they would be in a position to lay their eggs. Where would they lay their eggs? They would lay their eggs on the underside of the leaves, which by itself is an innocuous activity. It's just they're seeking shelter from predators by hiding their eggs away under the leaves. But what comes next really is is disaster to the plants, because in good time these eggs hatch out to become caterpillars. And what is the one thing that we associate caterpillars with? It's with eating, right? So often we are criticized by our family members as being caterpillars ourselves. If you have this tendency to limitlessly eat and put on weight. So caterpillars can often increase by a factor of their journey to become pupae and finally adult butterflies. And where does this 1,000-fold increase in mass comes from? It comes from munching on all the verdure around them, all the leaves that are abundantly available around them. And that's a death knell for plants, right? Because leaves are the food factories. That's the kitchen of a plant. So if you take down the kitchen, the plants are left without food. So plants on their part, have not been merely passive spectators which obediently succumb to this exploitation or decimation by the caterpillars. Some plants, including cabbages, I'm told, have developed this mechanism of controlling or curtailing the amount of damage that they suffer at the hands of caterpillars. So what they do is that they release certain chemicals, called terpenoids, and these chemicals are the SOS signals in some sense that the plants release, and they attract certain other insects which prey on these wasps. So there are certain prey on these caterpillars. So there are certain wasps which actually use these caterpillars in a very perverse way, which I shall describe in a little while. So the moment these wasps get a hit of this perfume, get a whiff of this perfume that the plants have released, it attracts them towards these plants. Then they go hunting for these caterpillars, and what they do next is they sting the caterpillars and they lay their own eggs inside the caterpillars. Now the caterpillar becomes a walking nursery. Okay, it's actually there's been a death sentence that has been leveled against it, because in good time the eggs of these wasps hatch and they eat the caterpillars from inside and kill them eventually. Okay, so as a consequence of attracting these wasps, these plants have exploited this very intricate feedback system to ensure that the number of caterpillars that are munching away at their leaves is kept in check. Okay, so this is a very strange and unlikely feedback control system that has evolved over millennia in nature. Of course, feedback is not the only way in which control is implemented. Regular feed-forward control also exists, although I have not highlighted it here because this course is concerned with feedback control. So, for instance, when you think of drinking a cup of coffee, you have a cup of coffee on a table and then you convey it to your mouth and you sip it and you put it back. Do you consciously think about doing it? No. But have you ever once, spilled coffee unless you were distracted in the process or something? No. Your hands, so if you have not admired it, I suggest you to do so the next time you drink it. Though they're so repeatably and with such fine control, they're able to clasp this cup of coffee, then they're able to convey it exactly to the location of your mouth in the shortest time possible with the least expenditure of energy probably, and then tip it at the right angle into your mouth so that the right amount of coffee is transferred into your mouth. Then carefully set it back in the right position and orientation so you don't tumble that hot cup of coffee onto your lap or something. So all of this is happening without you actually thinking about it, right? So in some sense, you might be led to believe that this is actually, there's no feedback involved here. But actually there was feedback, and that feedback happened when you were very young. So when you're very young, then you were still learning how to convey a cup of coffee to your mouth. You did make mistakes. You did take the cup of coffee the wrong way. But over a period of time, however, each of these wrong attempts acted as feedback.
Sir, your voice is breaking, sir. Your voice is breaking.
Sir, we cannot hear you.
My voice is breaking, is it?
Yes, sir. Yes,
Okay.
sir.
Okay. I don't know what I can do. Is this a little better? Or is it still breaking up? Hello?
Sir, actually for me it is breaking, but very little. I mean, almost I can make it what you are Thank you, sir.
Yes, sir.
Almost you can
I'm
almost.
able to hear it clearly.
So, okay, then maybe for those people for whom it is breaking, it may have something to do with the internet connection. Since I'm anyway recording this lecture, you can download this and watch it later. Okay. So I will continue now. You may please mute your microphones because otherwise I hear some static here. As I said, even in actions where you think feedback may not be involved, such as in conveying a cup of coffee effortlessly to your mouth, there was a learning curve involved. And every time you made a mistake, you paid attention to what mistake you made and you corrected for it the second time you did that same action. And over a period of time, you corrected to such a great degree that you didn't need to correct anymore. And you were able to mechanically do it. Okay. So this kind of control is iterative learning. So learning is to take lessons from that mistake, incorporate it into your memory, and avoid making that mistake the next time. And even there, feedback is involved. So having therefore paid the given the credit to Mother Nature, credit where it is due to Mother Nature for having invented feedback control well before human beings started to contemplate it. Let us now get into the human world. Let us go back several millennia to the first instances where feedback control was employed. And this was, it started maybe in 200 BC, so a really long time ago. That was when the first recorded instances of the use of feedback control can be found, through historical documents and so on. And the first control systems were used in the context of keeping time. Okay, so long before the mechanical clock came up, became popular. Of course, now mechanical clocks are also on their way out. You have electronic clocks, but before mechanical clocks were what were known as water clocks. So a water clock essentially is a cup which collects water from a certain tank. Now, if I were to release that tank, the water flow is more or less, the flow rate is more or less constant as long as the height of the water in the tank does not change too much. So the quantity of water that you collect in a cup is therefore indicative of the time, proportional to the time that has elapsed since you opened the tap, since you opened the valve. So this water clock was very widely used in the ancient world. In fact, I was just reading a little bit before preparing for this lecture, and I found that in courts and so on, they would keep track of the time necessary to handle each case by means of such water clocks. They would fill up a vase with water, and they would, the amount of time given to handle a certain case would be determined by the amount of time it took for the water to get emptied from that vase. Now, for cases which involve death sentences and particularly egregious crimes, they would fill up the water to a greater height, so that they would give the give it more time, give the case more time to be discussed. And in case some edits and deletions and some offline discussions had to happen, they would temporarily seal the exit to that vase until by means of wax until these discussions are completed. So water clocks therefore played a very important role in the ancient in keeping track of time. But as I already pointed out, as long as the height of water in the reservoir, in the tank, is not changing, it's the amount of water that is collected in a cup would be proportional to the time elapsed. But then we know from basic physics that as the height of the water in the tank reduces, the flow rate of water also reduces. And although the ancients did not know the physics behind it, they observed the fact that it was reducing, and they recognized the fact that they could not rely on the height of the water in a cup as an accurate indication of time if the amount of water that you are emptying from your tank was very large. Okay, so they needed a way to keep the height of water in the tank constant. Okay, and what they invented still finds use in our daily world. What they invented was the ball valve. Okay, so do you find ball valves in your flush tanks, in your toilets, and in your overhead tanks, and so on, they help to regulate the level of water in a certain tank. So how does the ball valve work? So when there's a floater, there's a balloon kind of a thing, something that floats on the surface of the water, which keeps tab on the water level. So when that water comes down, then this ball valve opens a certain wall and lets in more water. And as the water level goes up, then the ball valve also rises in height, and that causes this valve to shut automatically. So this helps to regulate the amount of water in this tank, and thereby ensure that at all times the flow rate of water out of this tank is a constant. In fact, the Greeks had perfected this technology, and they came up with what is known as a clepsydra. You see that on the left-hand side. So they had a very sophisticated mechanism of implementing this control system, which also had indicators and dials and so on, in a manner similar to a mechanical clock to indicate the time, and while keeping the level of water in the reservoir a constant. Okay, so water clocks actually had risen to amazing levels of sophistication in the ancient world, so much so that sometime around 1500 or 1400 AD, I don't remember exactly when Galileo was doing his experiments to understand the laws of nature, one of his great contributions are the equations of motion of an object under gravity, which we are all familiar with. So we are familiar with equations like U is equal to V is equal to U plus AT, where A is the acceleration and T is the time, and P and U are initial and final velocities, or S is equal to UT plus half GT square. So these are all equations that
Sir, your voice is breaking.
Objects on Earth move with constant acceleration when they are in the field. Is that true for everybody else also?
Yes, sir. Yes, sir.
Anybody else who's facing
Yes,
this?
sir.
We can't hear it properly.
Okay. We shall do one thing. I mean, I'll try to find a more reliable connection to internet next class onwards. So this class, you please suffer this discomfort of having to listen to my broken voice, because I don't know what I can do at this point. I can try to log off and log back in. Shall I do that? Let us hope that will improve matters.
Sir, actually, during the maths class also we had the problem. What sir is that he used to stop for a bit, maybe 2 or 3 seconds, so that he can ensure that the connection is back, good again in 2 minutes of time.
Okay. So is it better now? Are you able to hear me more clearly?
Yes, sir. Yes, sir.
Okay. All right. So I will continue. But what I would suggest is this class alone, you please listen to the recording, because I am recording. Hopefully, these problems will not be there. You download the recording and listen to it. In the next class, I will try to find a LAN connection or something with a not a wireless connection, and hopefully that will be more reliable or something. I don't know. I'll try to do something to fix this issue of poor connectivity. So I shall continue now. So as I was saying, Galileo used water clocks. So water clocks, were so precise. By the time Galileo came about, he used water clocks to obtain his laws of motion of objects through gravity. And motion of celestial bodies in the sky, and the time period of all of these, planets and so on and so forth. So in other words, the water clock played a central role in advancing our understanding of the natural world, in particular the celestial world. Okay, so the laws of motion due to gravity was how things behaved on Earth, and then all these time periods of planets, etc., had to do with astronomy. All of these advances could happen as a result of reliable water clocks that were available around that time. In fact, the water clocks have become so precise that even 50, 60 years after the mechanical clock was invented, even several years after the mechanical clock, people prefer to use water clocks because water clocks were still hand. It took quite some time to make the water clocks and make them obsolete. So, from 1680, these were among the few instances that could clearly be being noticed as options of feedback control. Our understanding of the natural world, or putting feedback control to good use for our practical, for our daily existence. So, around 1600 AD, industrial revolution had started in Europe, and industrial revolution involved, by definition, almost mechanization. In other words, getting huge machines powered by steam engines to do your work for you. And there were these big prime movers, as they were called, or self-driven machines, which could be used to do a lot of different activities automatically. Now, since these were by their very nature big, they had to be big because of the requirement to generate sufficient power, etc. You couldn't rely on a single human being, a puny human being, to control them. Okay, you couldn't depend on human strength alone to enable control of such self-driven machines. So, a lot of different mechanisms were invented to control such machines. One of them is a pressure safety valve, which was used for pressure regulation. The second was the float regulator, which was used to control liquid level. So the float regulator is not very different from the ball that we talked about in the previous slide. So it sort of became far more popular again in the between 1600 to 1800 during the Industrial Revolution. And then there was this very interesting contraption called as a centrifugal governor, which was used to regulate the speed of an engine. And on the right hand side, you see a schematic of this contraption, the centrifugal governor. This was invented by the famous James Watt, who also invented the steam engine. So this was just a landmark event because it was for the first time that the layman, the general public, became aware of the significance of feedback control. Because these kinds of governors used to be mounted on top of steam engines, and people could see them, rotating about and so on. So they could therefore that naturally piqued their curiosity about what these were useful for. Okay, so let me briefly describe how the centrifugal governor works. It's a very ingenious contraption intended to regulate the speed of an engine. So what you have in the centrifugal governor are two spherical heavy bobs, and you see them as two balls on either side of a vertical shaft in this figure here. Now what
able to see
happens is, pardon me?
Sir, we are in the old slide only.
Oh, you are not able to see this?
No, sir.
The slide has not changed, sir.
Okay, is it visible now?
Sir, what I suggest is me to log off once and logging in, sir. Would be better.
Okay, I shall do that then. Okay, I shall try that. Hello, am I audible now? Is my voice clear?
It's actually worse, sir.
Hello, can you guys hear me? It's actually
It's worse than last time. Yes, sir. Worse than last time.
Here. Okay.
Let
me do one thing. Let me simply go through the lecture. You can't hear us at all. You can't hear me at all, is it? I will try to log off again and then join in again.
Now we can hear you, sir.
hello, how is it now? Is my voice quality better?
Yes, sir, it's fine.
Yes, sir.
Okay. So then I shall again share the slide, and hopefully this time you would be able to see it. In this slide, I talk about the Industrial Revolution. Are you able to see that?
Not yet, sir.
Hello? Okay.
No, sir, not yet, sir.
Slide not visual yet.
So you don't see the screen also which I have shared, is it? Nothing is visible?
No, sir, no slides are visible.
Hello?
No slides are visible, sir.
Oh, let me try to share it again in that. Okay. Is it visible now? I have shared it again. Do you see anything from my screen?
No, sir, not yet. No,
Okay.
no, sir.
Sir,
Okay. So let us do one that case. Yes? Hello?
sir, could you log off your Wi-Fi connection and log in again? Might be that will be that.
No, let us do one thing. I shall do one thing. I mean, we can go on and that may work, that may not work. I will finish this lecture, okay? Even though you cannot see the slides, you just listen to me, okay? And even if you're not able to listen, to download and listen to the recording at some later point, because I don't know what might work, what might not work. You might end up taking a lot of time and not being able to find the right solution. So right now you're able to hear me clearly, right?
Better, sir, yes.
Then let me just finish the lecture, okay? We will try to find a better solution for the next class. Right now, let me just finish the lecture. Please excuse me if you cannot watch the slide. Hello?
Can you share the file now? We can see individually. That will.
I don't know how to share the file. Is it possible for me to post it somewhere or something? I don't know.
Sir, in the chat option, you can add the file and send.
Okay, let me try to do that. I will try to attach a file. Let me see if I can do that. File. I'm uploading it. I hope it gets uploaded though. It is taking its own time to upload. Okay. My suggestion is, I mean, once it uploads and you're able to view it, you please download it and watch it. But I will anyway separately, I think once it's uploaded, you will anyway be able to access it. And the recording also will be available to you, regardless of whether you are able to see it at some later point. Is that fine? So I shall, it's anyway being recorded. You please listen to it in case you are not able to hear it clearly. You listen to it at some later point. Is that fine? Hello?
Okay, sir.
So I got a message saying that the file upload is it didn't work out. So I will try to upload it again at some later point. Okay. I will convert it to a PDF and upload it at some later point. So let me continue with my presentation. So yeah. So I was talking about which was connected to levers, and that caused a series of other levers that caused the valve, which was supplying fuel to the engine to actually okay. So as the speed value centrifugal force, so they came closer to the central rotating shaft, and again this motion through a series of levers resulted in opening the fuel inlet valve a little bit more, so that some more fuel could be injected into the engine and increase its speed. So in this manner, it was possible to ensure that the speed of the engine was maintained at a certain set point. Okay, and all of these devices for pressure regulation, liquid level, maintenance, and speed regulation, and so on, were designed by engineers without actually appealing to any physical or mathematical understanding of what was happening. These were all very clever contraptions. I shouldn't say physical understanding, I should say mathematical understanding. These were all very clever contraptions which required a lot of skill and intuition and insight for people to develop. In fact, in those times, engineering was much more of an art than it was science. So these were all, in some sense, artists with a practical bent of mind, and they developed all these contraptions to help further the goals of the reason why mathematics could not be applied to understand these kinds of physical systems, because these physical systems generally obey differential equations, and differential equations require calculus to be developed before they could be applied. And calculus developed only in the late 1600s. It was invented by Isaac Newton and Leibniz in the late 1600s. And even after that, because of dispute over priority, the people in Britain believed that Newton had invented it first. The people in Europe believed that Leibniz had invented it first. So they weren't talking to one another for a really long time, as a result of this dispute over who deserved recognition for the invention of calculus. So that retarded the progress of the field itself and its application to various other physical systems. Okay, but eventually that did happen, and by 1800 people started to apply mathematics to understand the natural world around them, and in particular they also started to apply mathematics to understand feedback control of dynamic systems. Okay, one of the very first applications of mathematics to understand feedback control was done by an astronomer by name Airy. So the astronomers often want to look at certain specific parts of a sky, okay, and basically they want to keep staring at a certain star or certain other celestial object, and they want to compensate for Earth's rotation about itself while they are looking at this particular part of the sky. Okay, so what they therefore do is get this telescope to spin in the direction opposite to Earth's rotation, such that the telescope always stays pointed at a certain location in the sky. So Airy essentially invented such a contraption which could help him keep his telescope focused at one specific set of objects in the sky, despite the fact that the base on which his telescope was mounted, namely our planet, was going round itself once a day. So to do this, he used feedback control. Okay, he had some way of measuring speed and then correcting or measuring angular deviation and correcting for angular deviation by applying some control effort, by rotating the stage in the opposite direction. So what he discovered was that if the parameters of this mechanism weren't tuned very well, his telescope would undergo violent oscillations. Okay. Now, of course, we understand this in the language of stability and instability of the dynamic system, but for him, it was a matter of very great practical concern because these telescopes would contain very sensitive optical, their instruments, optical devices, and they would shatter if the vibration was too large. So, Airy applied mathematics to understand the origins of these oscillations, these violent oscillations, due to improper settings of his speed control system, and came up with a differential equation which could explain under what conditions these telescopes would become unstable. These telescopes with this automatic pointing control feature in them could become unstable. So this was the first time that mathematics was applied in the context of feedback control to understand why a feedback control system behaves the way that it does. And this was further strengthened. So in other words, differential equations were used to analyze feedback, and this was further strengthened by the great James Clerk Maxwell of the Maxwell's equations fame, who defined the criteria for a linear system to be stable. So under what conditions, for what kinds of values of parameters of a second order differential equation, a linear differential equation, will the system be stable? For what other values could it be unstable? All these were clarified by James Clerk Maxwell. And in the same century, the 19th century, we had one other, reclusive genius by the name Heaviside, who again contributed significantly to electrodynamics. And Heaviside introduced the notion of a transfer function. Okay, a transfer function is a concept which is used very widely in feedback systems in the modern world, but he was the one who introduced it first. Okay, so that paved way for an easy and intuitive understanding and analysis of the dynamics of a linear system. So these were the advancements that happened in the 19th century, and therefore we are sort of knocking on the doors of the 20th century now. So all these, if you see, were applications of feedback that were initiated by non-engineers. In the ancient world, of course, feedback found its engineering use in water clocks and so on. But in the 19th century, it was used. The mathematics that was used to understand feedback was primarily used for to further physics in some sense, and was initiated by physicists, Airy, Maxwell, Heaviside, and others. So this, as I said, brings us to the 20th century. And in the first part of the 20th century, people began to appreciate this notion of a system. Okay, to provide some historical context, it was around the turn of the 19th century that Charles Darwin, wrote his famous book on the origin of species. So people at last began to understand how and why the natural world has come to look the way it does. So he outlined all these famous principles, struggle for existence, survival of the fittest, and so on and so forth, which eventually result in organisms evolving to become whatever they are now. Okay, so this therefore cast what was earlier under the ambit of some mythology or some religious explanation. It changed the paradigm and allowed the natural world to be explained through a certain sequence of actions which naturally happen. Okay, so one could therefore think of inputs to the system, an output to the system, and some internal dynamics of the system, and so on and so forth. So this philosophical realization that we could view every other set of actions also under the ambit of a system was what was realized in the early parts of the 20th century. So you could talk of an economic system with its own set of rules, similar to how a biological system has its set of rules. Okay, so this notion of systems came out in the 20th century, and the utility of that was that if I were to understand the dynamics of a particular system in a particular domain, let us say in biology, and suppose the similar equations are obeyed in economics, then whatever understanding I have in biology, I can simply take it and apply it to economics. Okay, so as long as the systems have similar dynamics, the lessons learned in one of them can be applied to another. So this cross-disciplinary learning is possible if we recognize each of them as systems and recognize the commonalities between these different, otherwise apparently different systems. Okay, so that was one important breakthrough in the way we view, the knowledge that was gained in different, that was being gained in different fields, that was being acquired in different fields. The second, more tangible and practical advance that happened in the early parts of the 20th century was the invention of telephony, okay, and the birth of long-distance communication. And because telephony involved processing audio signals, frequency domain analysis became the norm. And in this context, there was one very important advance that happened. And this was in late 1920s, I think. And this was the invention of what is called as a negative feedback amplifier. And this was done by an individual by the name Harold Black. Okay, this was a very important moment in the history of feedback control, and probably you can trace the birth of modern feedback control to the invention of the negative feedback amplifier. It solved a very important problem that bugged telephony in those days. So let me describe the nature of the problem and how it ended up addressing the problem. Okay. So the negative feedback amplifier arose in the context of having to amplify or increase the power of these audio signals that were transmitted from one place to another place which was very far away. So to amplify the power, increase the power, they used what was known as repeater amplifiers. So they were called as push-pull repeater amplifiers, which were mounted every so many kilometers. So the power levels of the signal were boosted every so many kilometers. So in order to account for the attenuation that had happened in transmitting it from one location to another location much farther away. So these push-pull repeater amplifiers, however, were made of all these cathode, triodes and such other things, and they were highly non-linear devices. Okay, so and they also suffered from crosstalk. So a amplifier that used all these triodes and such other devices suffered from non-linearities, so they would distort the signal. Okay, so if there's a voice signal, it would get severely distorted, and there would be crosstalk as well. In other words, if me and my neighbor were both making a phone call, some part of my neighbor's conversation could be overheard by the person to whom I was making the call, and vice versa. My own voice would be heard by the person who actually was being called by my neighbor. So there was a problem of crosstalk as well. Now, a lot of engineering effort had been invested in improving the characteristics, the linearity, and crosstalk and so on of these repeater amplifiers, but without too much success. Okay, there was only so much that could be achieved by improving the hardware, and this proved to be a major stumbling block in widespread deployment of long-distance communication. It was in this context that Harold Black invented his negative feedback amplifier. So what he did, in fact, in the slide here, although you are not able to see the slide, I will. Are you guys able to see the presentation? Not yet, right? You're only able to listen to me, is it not?
No, sir.
Yeah. So you're only listening to me.
Can you reshare again?
Are you only able to listen to me, or are you also able to see my slides?
Right now, we only can listen to you.
Only able to listen to me. Okay, it's fine. You look at the slides after some time. I will upload them later. Okay. So the negative feedback amplifier, what I have done in this, what I'm showing in this slide right now, is a simulation that I did. where I assume that we have a nonlinear amplifier on our hands. Okay, so maybe it has some 10% nonlinearity or some such thing, and with cubic nonlinearity, let us say. Then if I apply a sinusoidal signal at its input, then if I were to pass it through a single amplifier, then the output signal doesn't look as distorted as one might fear, because the nonlinearity is small, it's only 10%. But you have to have many of these repeater amplifiers before the signal could finally be conveyed to the individual to whom it was intended. So what I have done in this simulation is I have cascaded maybe 20 or so of these repeater amplifiers and shown what happens to the signal as it propagates through this cascade of nonlinear repeater amplifiers. And what you see at the end of 20 amplifiers is a severely distorted signal. So what was initially a sinusoidal signal becomes a spiky looking, extremely distorted version of the initial sinusoid. Okay, so if I say something on one side, it could be unrecognizable at the other side of at the other end of the line. Okay, that was the problem that was confronting communication engineers around that time. So what Harold Black did was he took a small fraction of the output of this nonlinear amplifier, fed it back to the input, compared this small fraction with the actual reference, and any error between the two was suitably amplified before feeding back to the nonlinear amplifier. This was what he did. Now, if we repeat, let us say each amplifier was fitted with this kind of a feedback block, where you sample the output of the nonlinear amplifier, the voltage at the output of the nonlinear amplifier, feed it back in an attenuated form, compare it with the reference, and any difference is fed back to the nonlinear amplifier. What happens is when you implement this on every single repeater amplifier along the way, then when you pass it through 20 such repeater amplifiers, you see that practically all distortion gets removed as a consequence of this action of having feedback. And this can be revealed in the simulation, and you would see it in my slides as well. So, therefore, this was a huge achievement. Not only could you show that nonlinearity could be eliminated, it was also possible to show that crosstalk could be greatly minimized as well. So both the problems that were confronting widespread use of telephony, namely the problem of nonlinearity and the problem of crosstalk, could both be shot down with a single stone, namely by using the negative feedback amplifier. In fact, this strategy seemed so much like a silver bullet, so revolutionary and so important in its impact, that when Harold Black applied for a patent for his negative feedback amplifier, the patent examiners were unwilling to grant him patent. They thought that he had come up with some fiction. He was trying to sort of deceive them about the kind of improvements that were possible with his negative feedback amplifier, because the kind of improvements that he was showing were unbelievable. They were unconvinced that he had actually come up with a real working device. They thought he was trying to deceive them in some way with the kind of magical results in terms of improvement of linearity and crosstalk and so on that he was able to show. But eventually he did get the patent, and the use of feedback control started to gain traction in the 20th century. Now, with this negative feedback amplifier in place, electrical engineers pounced upon it, did further research on feedback itself, and they understood what were the essential elements required for implementing successfully a feedback system. So what they realized was that you needed to have a way to measure the output of the system that you are trying to control, then compare it with the reference or the signal that you want the output to mimic, and then any error between the two had to be fed to what is known as a controller, which was a high gain function. So what we mean by high gain will become evident later on in this course. Okay, so this basic structure of a single input, single output feedback system became clear, and a lot of important advances were made in the design and analysis of controllers for feedback systems. And many of the big names that you might have come across in your undergrad, including Nyquist, Bode, Nichols, and and so on, made their contributions around this time. So Bode plots, Nyquist plots, root locus, which was invented by a person by name Evans, all of these took their birth around this time. So this was in the 1930s and early 1940s. But to a large extent, despite all these advancements in the theory and understanding of the mechanism of feedback control, the applicability of feedback control was restricted primarily to the electrical engineering domain. And that is because to implement feedback control, you need to have sensors which measure the variable that you are trying to control. Now, unfortunately, around that time, there weren't enough ways to measure these variables, and more importantly, there weren't enough techniques to convert these measurements to electrical signals, because feedback control is most readily implemented using electrical circuits. Okay, so there was no way to transduce a mechanical signal into an electrical signal effectively. But all this changed in the 1940s. What happened in the 1940s? You had the World War, the Second World War, and in the race to win the World War, people recognized the importance of machines. So there was, and the control of machines. So there was an explosion in the number of sensors that were developed in World War II. For example, the gyroscope and many other inventions, radar and so on, were all invented during the Second World War. And these sensors, therefore, made available important information about the physical state of a particular machine, either its speed or its tilt or its angular velocity or its distance. All this information became available. So now that you had this information, you could then feed that to your feedback system and ensure that you are able to control each of these in the manner that you want. So, as I said, the gyroscope, and there is something called the Norden bomb sight, which was intended to accurately target a location that you wanted to bomb. This was developed during the Second World War. And then there was the radar. All of these were developed, and as a consequence, feedback control also expanded its arena of applicability. Some new techniques were also invented. For example, the very famous proportional integral derivative control, or PID control, which is something we will talk about in this course as well, was invented during this time and was used to control ships. Then frequency domain analysis became the norm. So people had already worked on frequency domain analysis in the telephony era, and these were borrowed en masse by people designing control systems for controlling ships and aircraft and all sorts of other vehicles. Okay, so there was a huge shot in the arm that feedback control got as a consequence of World War II. Just give me a moment, I'll drink some water. And that brings us to 1950s. And just as World War II was ending, a Cold War between the erstwhile USSR and United States was hotting up in some sense, figuratively. And along with Cold War came this, competition for control of space. Okay, so when you think of controlling something in space, for example, a satellite or whatever else, or a spacecraft more generally, these spacecrafts can easily change their orientation, their moment of inertia can change, and so on and so forth. So the equations governing their dynamics are essentially non-linear. Okay, they are not linear differential equations, they are non-linear differential equations. Okay, all this time people had developed these frequency domain techniques, and frequency domain techniques are applicable primarily to linear systems, not so much to non-linear systems. So there was this need to control spacecraft and other such non-linear systems, and there was this inadequacy associated with available control technologies. I mean, the literature that was existing about feedback control up to that point. So that was one constraint. The second constraint was that when you talk of controlling spacecraft, you also need to think about economizing fuel consumption. Okay, you don't want to spend too much fuel in moving something from point A to point B, in changing the orientation of a spacecraft and such other things, because fuel is very precious. So, therefore, this led to further development in controls itself. So, it led to, for example, the development of optimal control. So, how do you move something from point A to point B in such a manner that the fuel consumption is minimized? So, what is the optimal trajectory of moving something so that fuel consumption is minimized? So, these kinds of problems became practically very important. Of course, people realized that you did not need to limit yourself to just minimizing fuel consumption. You could optimize some other, functional also. But this was a start. And because systems were non-linear, the systems you were trying to control were non-linear. You couldn't any longer depend on, frequency domain-based design and analysis techniques. So people developed, state space-based description of a system. The state space-based description is essentially a way of representing a dynamic system as a first-order vector differential equation, and that has some unique advantages in terms of its ability to be solved easily. So, if, for example, Runge-Kutta techniques and others can be used to solve such equations effortlessly, and people adopted that formalism to also develop control systems using that formalism. So, this time domain control became very important during this time, from 1950s to 1980s. But the scope of what could be done was not as expansive, because sometimes these control systems require fairly sophisticated control laws, or in other words, some fairly sophisticated mathematical equations had to be implemented to realize the objectives of control. And it couldn't be done in a very straightforward manner using electronic circuits, using amplifiers and passive elements and so on and so forth. But all this changed around the 1980s with the growth in computers. Okay, so people now had a way of implementing these sophisticated control laws, which could address fairly challenging problems of control, including nonlinear control and so on. But there wasn't good hardware available up to that point to realize these control systems. So digital control, therefore, captured the imagination of researchers and engineers alike, starting from 1980. Okay, so people figured out how to implement a control system with a computer, figured out what consequences there would be to that implementation, how to minimize the effect, some negative effects of that implementation, and so on and so forth. And with the development of digital control, nonlinear control schemes, which earlier, as I said, could not be readily implemented using electrical circuitry, could now be effortlessly implemented. And that became a huge source of inspiration for controls theorists. So lots of different control strategies, such as adaptive control, nonlinear PID, some industrial process control like model predictive control and so on, could all really take wings as a consequence of the availability of a computer to realize these control laws. And many of them were also applied very widely, in particular in robotics. So robotics is one area where the dynamics is highly nonlinear, and your control laws also have to correspondingly be nonlinear for you to be able to control a robot. And all these nonlinear control schemes found a ready test bed in the form of the robots that needed to be controlled. Industrial robots, humanoid robots, and so on and so forth. Okay. So that brings us to the end of this survey of the history of feedback control. I just wanted to make some comments before I conclude this, lecture. If you just look at the way in which this body of knowledge was employed by people during the different times in history, from around 200 BC till 1600 AD, okay, it was used primarily to further human curiosity about the natural world around a human being. Okay, you wanted to understand the laws of physics, you want to understand the motion of planets, etc., etc. All of these became possible as a consequence of using feedback control in the context of water clocks. Okay, so it was therefore it served in some sense a rather noble purpose of whetting human curiosity and helping human beings understand the natural world around them much better. Then between 1600 and 1800, or maybe even 1900, it was used during the Industrial Revolution. And Industrial Revolution was not as non-controversial as the use during Industrial Revolution was not as non-controversial as in the earlier era. That was because, on the one hand, of course, it resulted in development of the trains and engines and mechanization and so on and so forth. But it also resulted in expansion of colonies of these industrialized countries around the world. And being in India, being a colony, a former colony of Britain, we have been taught all too well the mass suffering that Indians had to inflicted or had to suffer during the Industrial Revolution. The way the local industries were decimated, the way raw materials were taken away, plundered in some sense from our country at exceedingly low prices in order to fuel the Industrial Revolution and so on. So there was definitely a negative aspect to Industrial Revolution in terms of the exploitation of people in the colonies from which these raw materials were being sourced. But at the same time, there was also the positive angle to it. So along the way, in our own country, railways were introduced and mechanization was brought in, and that helped connect people in several different ways. And therefore, there were also positive consequences of Industrial Revolution, and therefore indirectly also positive consequences as the result of deploying feedback control and making them relevant to our world. So if you come to the 20th century, if you look at the examples of instances where feedback control has really grown, most of them have been in the context of wars. Okay, except for telephony, which was a very benign application. Most of the advancements in feedback control happened during World War II and subsequently during the Cold War, and subsequently again further automation and further computerization, etc., that happened during the Gulf War in the 1990s, and so on and so forth. So right now we are in a situation where we are afraid of drones, taking over battlefields. So instead of people fighting wars, people can be sitting comfortably in their houses and they can be remotely flying these drones to shoot down people in another country. So this has already been done by Americans, where they have flown drones over Afghanistan and shot down people. Okay. So what is saddening to contemplate is that increasingly, feedback control has been employed in the context of mutilating, killing one another, and making our world a less secure place. Okay, so earlier it was used to whet our curiosity. Then it was used for development, for industrialization, for mechanization, automation, and so on. And in the 20th century, all advancements can be linked to wars. Okay, this, at least to me, is a sad trajectory for the subject to follow. But any subject is neither good nor bad in its own right. The way in which we apply them is what makes a difference, is what makes a subject a harmful one or a benign one in the long term. Okay, so the way we employ these otherwise value-free tools of control systems, all these control strategies, etc., are in our hands. So it's for us as engineers to decide how we want to deploy this knowledge. Okay, whether we want it to further the agenda of armies and others around the world, or we want to use it for something else. That's a decision that we individually have to take at a personal level. So this is one concluding remark that I wanted to make. And the last point that I wish to make was that going forward, one of the most important issues that will probably dominate discussion in the 21st century is climate change. And this also, ironically, has some connection with feedback control. But this time it is not negative feedback, but it is positive feedback. So if you have increase in carbon dioxide or greenhouse gases in the atmosphere, then it will result in melting of snow or ice in the Arctic and Antarctic regions, and that will result in release of further more greenhouse gases. That's one thing. And if there is that much lesser ice, then sunlight is not reflected as efficiently by water as it is by air. So as it is by ice. So that sunlight will be absorbed even more by the water, by Earth. So that will result in further increase in temperature and so on and so forth. This sets up a positive feedback loop, which results in growth of temperature and will place the lives of practically every one of us at risk. It is a pity that it's not being discussed with the urgency that it deserves, but nevertheless, it is worth noting that this would be the dominant issue of the 21st century, maybe alongside the nuclear weapons or some such thing. And you have feedback also at the heart of climate change. So I have termed this latest feedback no control as a consequence of the fact that it will drive us headlong towards disaster if we don't realize its significance on time and take appropriate corrective actions. Okay. So with that, I come to the end of this lecture, this popular lecture on feedback control. So I don't know how much of this you were able to see, maybe very little, because you said that the slides were not visible from very early on, but the recording is there. Hopefully the recording will also include these slides, so you can take a look at it. So do we have any questions in the meantime? Okay, so I don't see any questions. So what we shall do is we shall stop this lecture at this point. So thank you very much.
Thank you, sir.
Yes.
Thank you, sir.
Yeah.
Excuse me, sir.
Thank you, sir.
Sir.
Thank you. Thank you. Yes.
Sir, audible.